Let's run through a few quick examples of derivatives of functions involving logarithms, so you can see a couple of the ideas that come into play here. Suppose first we have the function f of x equals the natural log of the tangent squared of x, and we want to find its derivative f prime of x. If you check the derivative laws introduced in this section, you see that the derivative of the natural log of a function is 1 over that function. You can confirm that for yourself with implicit differentiation. I recommend you work through that. It's worked out in the textbook, but you can try that for yourself. It's nice to know that you can work through these things for yourself. If you ever forget the rule, you can re-obtain it. So we have 1 over the tangent squared of x, but of course the chain rule comes into play here. Since this is not simply natural log of x, there's a more complicated function. So we need to multiply this by the derivative of the tangent squared of x. So we have a function squared, so the power rule tells us that that is twice that function. We have 2 tan x. And then the chain rule is applied again. The derivative of tangent is secant squared. And that takes care of those expansions. Now this is a common pattern we see where the derivative of a natural log is 1 over a thing times the derivative of what's inside. So what we will often do actually is go straight to that. Basically we would say, okay, well, we know we're going to have the tangent squared of x in the denominator. And in the numerator, you can see what happens here when we multiply this through. We have this stuff gets multiplied into the numerator, and we have the 2 tan x secant squared x. So you could go straight to this form, the second step, if you're comfortable doing that. And then once you have that, you should take a look to see if anything algebraically simplifies. In this case, we have a factor of tangent in both the numerator and denominator. So we can simplify that down to twice the secant squared of x over the tangent of x. And if we think for a moment here, the secant is a 1 over cosine, and the tangent involves a division by cosine. So let's, actually I can just move that to the right. This is 2 secant squared x cotangent x. And that might make it a little bit easier to see what happens here, because the cotangent would, of course, be the cosecant divided by the secant. And that means that one factor of secant cancels out, and we have 2 secant x cosecant x as probably the simplest form of this derivative here. It's probably the easiest way to write that. But the main idea, again, is the derivative of a logarithm. You will have 1 over that thing times the derivative of that thing by the chain rule. So we'll very often just kind of tuck that into the numerator. For a second example, let's take a look at the log base 5 of x e to the x. Now, for this, we need to use the first derivative formula that the textbook presents for a general log base b or log base a, whichever they use there. And that looks like 1 over the inner function, in this case x e to the x, times the natural log of whatever the base is. Here we have natural log of 5. The general formula has that natural log of the base in there, but if you're starting with a natural logarithm, your base is e, natural log of e is just 1, so that seems to vanish when we work with derivatives of natural logs. But at any rate, we now have to multiply this by the derivative of what's inside. And I'll just jot it like this for now, because I wrote this fraction first to illustrate clearly the pattern that we have, but just as with the other logarithms, what we'll often do is say, okay, well, the argument of the logarithm is going to be down in the denominator, along with, in this case, a natural log of 5 to take care of that base. And the numerator will be what the chain rule tells us, which is the derivative of x e to the x. So taking the derivative of x first, we're using product rule here, of course. Derivative of x is 1, so we have e to the x plus x times the derivative of e to the x, which is e to the x. So we get that. We see there's a factor of e to the x and everything, so we can cancel that out, and we are left with 1 plus x divided by x times the natural log of 5. So again, always make sure to look to see if anything simplifies. If you have a common factor you can pull out of everything, you should do so, and break that down as far as you can. For a third function here, we have the natural log of the absolute value of the cosine of the natural log of x. Okay? So, y prime here will be, well, we have a natural log of a function, rather the natural log of an absolute value of a function. And one of these statements in the textbook is also that the natural log of the absolute value of x is 1 over x, just as the natural log of x is. We have a nice symmetry around 0. So we can still use the technique where we take the denominator, and rather we take the argument and tuck it into the denominator. This one is actually going to, I'm going to go ahead and write that one out separately rather than putting it in, so we'll see what happens here. So now we have to take the derivative of the cosine of the natural log of x. Well, the derivative of cosine is negative sine. So we have the negative sine of the natural log of x. But now the chain rule applies again, and we have to multiply by the derivative of what's inside once more. So we have 1 over x. So now let's bring these together a little bit. You see why I didn't want to tuck this into the numerator. I knew that we would have this 1 over x, and that gets a little bit clumsy. But this makes it clear we can multiply through in the denominators. We have x times the cosine of the natural log of x. The numerator contains only the negative of the sine of the natural log of x. Again, we look for anything we can simplify. We have a sine of something divided by the cosine of that same thing, and that will be the tangent. So you see we have the derivative of this function works out to be the negative of the tangent of the natural log of x, all divided by x. Okay. Hopefully you're getting a hang on, kind of getting a handle on how that works, getting the hang of this. Let's finish off with exercise number 24 from the textbook. Y equals the natural log of the square root of 1 plus 2x divided by 1 minus 2x. Now, that might look much less pleasant. You can imagine, okay, well, you'll have 1 over the derivative of that. Sorry, you'll have 1 over that times the derivative of that, and the derivative of that, you'll turn it into like a fractional power, and then you have a chain rule, but there's a quotient in there, so you have quotient rule. This is starting to sound like a mess, right? But do not forget properties of logarithms, which hopefully you have learned thoroughly and extensively in previous courses. This is the natural log of 1 plus 2x divided by 1 minus 2x raised to the 1/2 power. And one of the properties of a logarithm allows us to write that as 1/2 times the natural log of 1 plus 2x divided by 1 minus 2x. And that, we have a logarithm of a quotient, and that we can break apart into a difference of logarithms. So the natural log of 1 plus 2x minus the natural log of 1 minus 2x. And we could leave it like this, or if you want, you can distribute that 1/2 through. You have 1/2 times the natural log of 1 plus 2x minus 1/2 times the natural log of 1 minus 2x. And following this chain of equality back, you see this is just this is just another way of writing what we started with. We haven't taken a derivative yet. This is just algebraic manipulation using the properties of logarithms. I showed every single step in here, step by step, to refresh your memory. Hopefully you were familiar enough with these that you could do this in fewer steps. If not, maybe go back and practice some of your work with logarithms. That'll be very important. But by doing this, we see y is equal to this last expression. So now when we take the derivative y prime, we have 1/2 times the derivative of this logarithm, well, that'll put 1 plus 2x in the denominator, and the numerator will have the derivative of 1 plus 2x, which is 2. We have minus 1/2 times the derivative of this logarithm. That puts 1 minus 2x in the denominator. And the numerator is the derivative of 1 minus 2x, which is negative 2. So we see, okay, 1/2 times 2 is 1. We have 1 over 1 plus 2x. We have minus and negative, that'll make plus. And again, the 1/2 and 2 cancel, and we have 1 over 1 minus 2x. And this is an acceptable form for the derivative. In this case, I don't think it's quite the best form. You could leave it like this if you want. I think it's a little bit nicer if we take a look at this and say, oh, wait, hold on. If we were to get a common denominator here, we would have 1 minus 2x plus 1 plus 2x divided by 1 plus 2x times 1 minus 2x. And that, you see the minus 2x and the plus 2x cancel. We have 1 plus 1 is 2 divided by, and in the denominator we have a product of a sum and a difference. So that will be 1 minus 4x squared. And this, I think, is a slightly better way of writing it. I would say that this is simpler and probably the best answer. If you did leave it like this arrangement over here, I would say that's probably fine also. But for most purposes, simplifying it down to here would be better. But yes, you can see that. Now, you could, of course, take this derivative directly. Take the derivative of the natural log, have 1 over this thing times its derivative, use the power rule with the 1/2 power, using chain rule repeatedly along the way, apply quotient rule to this thing, and then try to simplify the massive algebraic mess you're going to end up with. But if you use a couple of log properties right up front, you get a much simpler expression. It's longer, right? This thing right here is maybe longer and perhaps a little bit harder to get an intuitive grasp of what's happening than what we started with, but it's broken up into a bunch of very small, simple pieces that are individually much easier to take derivatives of. So then when we take our derivative, computing the derivative is one single step, and then a very simple step of simplification to get to something that's reasonable, and that's fine. And like I said, if you do want to combine it together to make it even more compact, that's nice, and that's a fairly quick and easy operation as well. So using your log properties when the opportunity presents itself can be very useful. Simpler expressions, you may find that you can use log properties or not. If you go back to the first two examples I showed in this video, each of those you could begin by simplifying with a logarithmic algebraic property. And I recommend that you try that on each of those, see what you can do algebraically to simplify the expression first, and then take the derivative and confirm that the derivative you get is the same as what I obtained taking the derivatives directly. Compare them and see which you like better in which circumstances. Relatively simple expressions like those first two, it often doesn't matter too much. It's largely a question of preference. But try that out and see what you think of it. Certainly when you get into the much more complicated expressions like what we have here, these are much easier to approach if you apply those log properties up front. So, exponents, radicals, multiplication, division, all of those are things that we have nice logarithm properties that allow us to turn them into different versions of themselves that are much easier to work with as far as derivatives are concerned. And that is actually the idea behind logarithmic differentiation, which I will cover in a separate video and is discussed in its own subsection in the textbook. But if all of this is making sense to you now, if all of this is making sense to you so far, try some exercises with just simple derivatives of logarithms. Make sure you see how those work. And as soon as you get the hang of that, you can move on to the logarithmic differentiation.